All right. Today we are in chapter 10, section 2, and we are talking about the laws of motion. With the laws of motion and in physics, a lot of the work is attributed to two men. You've probably heard their names, Galileo and Newton. All right. And Isaac Newton is probably slightly more famous. He presented his findings in a book called Principia. It has a bit longer name than that, but the shortened, accepted name is Principia. Okay. And in this writing, he gave us the laws of motion. All right, there's a couple laws of motion, and we're going to dive right into the first law of motion. Okay, the first law of motion, you've probably heard this one before, is that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an outside force. Okay, so an object flying through space with nothing affecting it will fly through space forever. All right, an object sitting still, unless something pushes it, will stay still forever. All right. These are his findings. Now, an example of this that you can find pretty easily is if you take a cup, okay, and on top of that cup you put a quarter and a card. So if you had like a cup and you put a card on top of it, and then set a quarter on top of that, okay. And you set my quarter, but set a quarter on top of that, all right. And then you quickly move the card, all right, without throwing the quarter or anything like that. The quarter will drop straight down. Because you're not putting force on the quarter itself, you're putting force on the card. Pull it out, the quarter goes straight into your cup. Okay, and this law in general can be described by the word inertia. All right, and this is kind of the tendency for an object to keep doing its thing. If it's moving, to keep moving. If it's sitting still, it's more technically defined by the resistance to change in motion. All right, the second law of motion will give us our first formula. Okay. Second law of motion states that regardless of the acceleration of an object, okay, the force required to accelerate an object is equal to its mass times the desired acceleration. Okay, so think about it. If you wanted to push a car and speed a car up, it's a lot harder than if I want to speed this cup up, right? I can speed this cup up pretty easy. Not a lot of force required. It's sped up and flew off. All right. If there was a car here, I would be really pushing on that car to try to speed it up. Right, I had to lean into it and give all my energy. Okay, so the force required to accelerate an object, all right, is equal to the mass, how heavy the object is, all right, times the amount of acceleration you want. Okay, so force, all right, equals mass times acceleration. Okay, now. It is not a bad idea to start a formula sheet, okay? In a lot of physics classes, a lot of science classes, you will be allowed to have a formula sheet, even when it comes to a test, okay? There's so many formulas, and there's so many things going on that a scientist is more productive by being able to use any formula rather than just having a bunch of formulas memorized, right? So the key here is understanding how to use this formula. All right, so force equals mass times acceleration is our formula. All right, we're going to take a look at the third law of motion. Okay, this might be the most famous law of motion. I'm sure you've heard of it at this point, and it is that every action has an equal and opposite reaction. Okay, that's the third law of motion. What does that mean? All right, that means when you push on something, all right, that object is pushing back on you the exact same amount. Okay, so example of this: if you hit the wall also technically hits your hand, right? That's why your hand would get sore if you hit a wall, right? If you are pushing on something, right, it is equally pushing back on your hands. That's why you feel the object when you push on something, right? Because not only are you pushing it, but it is then pushing back on you, okay? Example of this is a spaceship taking off, okay? The spaceship doesn't just magically lift off and fly through the air, right? It applies a force straight down very hard with this rocket. It throws literally energy and mass out the bottom of the rocket, and then the air, the gas, pushes that exact same force back up on the rocket. The rocket takes off and flies up into the sky. Okay, this is the third law. Okay, every action has an equal and opposite reaction. Okay, now we know that these are equal and opposite reactions. All right, but there is some point where the forces become unbalanced. All right. Example of this is if I want to move something. Okay. If I am pushing something, right, and moving it, right, the force that I apply to it and the force that applies to me are equal. That's the equal and opposite reaction. But I am giving extra force past that. All right, there is a force past that it can't push back on me. All right, that translates into motion. Okay, I'm adding energy to the object. I'm moving the object. I'm accelerating it. This is an unbalanced force. All right, so if you're pushing on something that's not moving, balanced force. Meaning you're pushing equally, it's pushing equally. There's no additional force from either side that's being applied to overpower either side. But unbalanced force is when one side has more power available and therefore it can push the other side. All right, the force to contact is still equal, but there's additional force behind one side that's allowing it to move the other object. All right, so that's balanced and unbalanced forces.